Alright, hello and welcome. The purpose of this video is to go through another problem where you can use the squeeze theorem. So here the problem is to evaluate the limit as t goes to 0 of the function of t, so t is the input right now, and the function is t to the fourth times cosine of 1 over t. So here's how we're going to do this. This looks like the question at the end of class. We're going to use the squeeze theorem. So first, I'd like to just use this fact from trigonometry that cosine of z, no matter what z you're looking at, is between -1 and 1. So this is true for all real numbers z. And then what I'm going to do is just plug in z is equal to 1 over x. So that turns into this inequality, or really this double inequality. So -1 is smaller than or equal to cosine of 1 over t, I'm plugging in z is equal to 1 over t. Cosine of 1 over t, and that's smaller than or equal to 1. And then I can take all three sides and multiply by the positive number x to the fourth. Now that even 4 in the exponent, if I multiply by t to the fourth, that 4 guarantees that what I'm multiplying by is positive, so no inequalities flip in order, and then each of these three sides multiplied by t to the fourth gives negative t to the fourth is smaller than or equal to t to the fourth times cosine of 1 over t, which is smaller than or equal to t to the fourth. So we get this fact, and it's true for any number t except for 0. And so with the way that the squeeze theorem goes, I'm actually going to now take this thing here and call this f of t, take t to the fourth right there, and that will be called h of t. So h of t will be positive t to the fourth, f of t will be negative t to the fourth, and that squeezed in function in the middle is going to be g of t. So g of t is t to the fourth times cosine of 1 over t. Alright, so that's one fact that we needed. What we've just established here by naming these functions f, g, and h is we just established that f of t is smaller than g of t, which is smaller than h of t for all t which is not equal to 0. So that's the first requirement for the squeeze theorem that we've established. The second thing that we're going to need is actually now take these functions, let's just rewrite them here. So f of t was negative t to the fourth, and h of t was t to the fourth. Now these are different functions, but since they're both polynomials by DSP, by using the direct substitution property, we actually get that the limit as t goes to 0 of f of t is equal to f of 0, which is negative 0 to the fourth, or just 0. And then the limit as t goes to 0 of h of t is h of 0, again by DSP, and this is equal to 0 to the fourth, or just 0. Now since these two things match, the second requirement to the squeeze theorem is met, which means now the two requirements for squeeze theorem have been satisfied. So now we can say by the squeeze theorem, we get this, that the limit as t goes to 0 of g of t is also equal to this number 0. We copy that there. And in fact, g of t, what was g of t? If you go back to this last page, g of t was a function that we wanted to find the limit of. So actually, just by plugging that g in, this statement, just writing it in other words, we actually get limit as t goes to 0 of t to the fourth cosine of 1 over t is equal to 0. So the only difference between these two is just replacing g of t with what it's equal to, namely t to the fourth times cosine of 1 over t.